All right, so this is the continuation of 8.5 geometric series. Oh no, zombie attack. There is a zombie outbreak in your area. The first week there is only one zombie. So that would be the first term. G sub 1 is 1. But each additional week, the number of zombies increase by 25%. So that would be 1 plus 0.25. That would be that ratio. 1 plus 0.25 represents those who have the disease but have not yet reanimated. Use sigma notation to express the total number of zombies at the end of each week. Okay. So going from 1 to n, first term is 1, and then we're multiplying by 1 plus 0.25, or I could just put 1.25, and that would be to the n minus 1. Since this is the first term, this is n minus 1. If this was the 0 term, this would just be n. How many zombies will there be at the end of 10 weeks? Okay, so I'm going to use my summation for a geometric series, which is g sub 1 times 1 minus r to the n, all divided by 1 minus r. So let's see, that's going to be s sub 10. The first term is 1. 1 minus this whole thing is r, so 1 minus 1.25 to the 10th. Notice these should always match. All over 1 minus 1.25. Calculator. 1 parentheses 1 minus 1.25 to the 10th. And then I'm going to divide that by, in parentheses, 1 minus 1.25. And I get 33.25. So between 33 and 34 zombies. Let's look at number 4. The Earth's population in 2009 was 6,790,000,000 and growing at a rate of 1.188% each year. So that would be 1 plus, because it's growing at that rate, 1 plus, I'll move that over 2 places, 0.01188. That would be my constant ratio, because I have the starting amount plus I'm growing at this rate, so I'm adding that. I express the population n years after 2009. So 2009 is the starting year, so this is going to be like the 0 term. So G sub n is 6,790,000,000 times the 1.01188 to the nth power, because this is the starting amount in 2009, not after a year. Therefore, this is simply to the n. Question B asks me, during what year will the model predict that the population will reach 10 billion? Well, what I'm going to have to do is I'm going to have to use my table. I'm going to go to y equals and put in the 6,790,000,000 times 1.01188 to the x. And then I'm going to pull up my table looking for 10 billion. And let's see, 10 billion. I'm wondering if they're going to write it in scientific notation. So I'm writing this out so that I know how to look for this in the table. So let's first go to y equals and put in the 6,790,000,000, 1.01188 to to the x power. Let's make sure I put in the right number of zeros. 1, 2, 3, 4, 5, 6, 7. Good. Then I'm going to go to my table. Now notice it says e to the 9. That means I'm going to move it over 2 places and add 7 zeros. And so if you moved this number here, we were, let's see, 1, 2, 3, 4, 5, 6, 7. So they're probably going to have 10.00 e to the 9. That would be 10 billion. So let's look for that in the calculator. There we go. Or just 1 times 10 to the 10th. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, that's 10 zeros. So 1 times 10 to the 10th would be 10 billion. So it happens right there at year 33, 34. And I guess it goes enough above the 10 billion, but they just want to know in what year will it reach 10 billion. It reaches 10 billion. Sorry, you can't see the table. I apologize. It reaches 10 billion right here, and then it doesn't get till it's 10 or 11 billion until right here. So in year 33, it reaches 10 billion. Year 33.